Hey everybody, welcome back. Mr. Smith here. Now you're not going to be surprised to hear that people generally view radiation safety as a topic that's somehow a little different from safety in general. And in fact, it is a little bit different. Radiations oftentimes are things that we can't see. And what I wanted to do in this deck is to break down all of the mysteries that go into radiation safety and show you how it really fits into the topic of safety in general. You've got a radiation worker on the left, so this fellow right here is using a Geiger counter to sample the exposure that this to see if he's carrying any particles on him actually on the outside of his suit. Whereas this individual right here, this technician, is actually looking at the exhalations of the man in the middle, and what they're doing is looking for any radon gas that he might be expelling from his body. And we'll talk about why that's a particularly scary thing to have done. But so radiation, right? It's a thing that you can carry around on you that continues to expose you even after you think you've left the area. And you could even carry it around in your body. So there are some things about radiation exposure that are potentially a little bit worrisome. So what we're going to do is to start by talking about the first of four things. To understand radiation safety, the first thing you have to understand is that not all of the bullets that are being shot out of radioactive isotopes are the same. So they don't all carry the same energy. So polonium-210 source shoots out alpha particles on the average with 5.3 MeVs of energy. That's a lot. Beta particles are zero point 0.5 MeVs. That's a factor of 10 less. You have gamma sources that are about 2.5 MeVs on the average. That's thing one. They don't all carry the same energy. So thing number two, if you're exposed to radiation coming from a point source, simply getting away from it physically could be the biggest thing you would do to lower your exposure. And here's why. We know that whether it's sound coming out of a loudspeaker or light coming out of a light bulb, the intensity of anything coming from a point source spreads out and fills the surface of a sphere. So the surface of a sphere follows this formula right here. 4 pi r squared. So what we're going to see is that from a point source, if you double the distance that you are away, you get a quarter of the radiation, triple your distance, you get a ninth of the radiation, and so on. Okay, so that's very important. The exception would be if the radiation is literally coming from everywhere. It's called background, and then moving doesn't matter. But generally what we're worried about is we're talking about point sources of radiation, so that's a big deal. The third thing is that not all kinds of radiation behave the same. So what we've done here is drawn up a table called the quality factor, or QF. And what they've done for comparison's sake is to assign X-rays and gamma rays a quality factor of 1. And you'll notice that beta particles, fast protons, they're basically the same. So what's going on with this that it would explain why slow neutrons, fast neutrons, and alpha particles would be so much more damaging in human tissue, even when they carry the same energy as X-rays or gamma rays? Well, here's what it is. The thing to understand, if I draw a really crummy and blobby example of skin, is that skin is made of ultimately positive and negative particles. We have protons inside the nuclei, all surrounded by negative electrons, and so on and so on and so on. And so what you want to picture is that if the odds of radiation interacting strongly are very high, it's going to be more damaging and get a higher quality factor than a radiation that's not going to interact as strongly. So here's the deal. X and gamma rays are electromagnetic. They're not particles. They don't have mass. And so what happens very often is that X and gamma radiation are waves. They'll travel through flesh, there's my gamma, without interacting with anything. Or if they do interact, they'll interact with an electron, and an electron will go off and do its own little damage. The thing about a neutron that makes it unique is that it has no charge. And what happens is, because it has no charge, it can penetrate the positive core of nuclei without being repelled. And so that that neutron rather, can ping out, can knock out a proton, which then goes and, for the reasons we talked about, because it has charge, will interact with other things. It will interact with electrons and drag them along and create destruction. But it will continue to do so. The neutron will do one interaction, free up a proton, and continue right on through after it scatters and do another collision and another collision. So depending on the speed and energy of the neutron, it can be literally like a bowling ball wrecking through bowling pins in the body. And for a very similar reason, heavy ions and alpha particles can be similar. There's something that deserves to be said about alpha particles. Alpha particles have a +2 charge. And you should know this from our studies in the lab. Alpha particles are not something that we really worry about shielding ourselves from. Our skin is actually sufficient shielding against alpha particles outside our body. Why? They have a +2 charge and they have a lot of mass. So they're going to interact very strongly with atoms and molecules that we are built from. In other words, they kill skin cells on the outside of our body. But the skin cells on the outside of our body are used to being exposed to radiation. That's why they replace themselves so often. So exterior damage from alpha is not generally a big worry. What is a big worry is if you have, for example, radon gas in your basement. If you live in New England, it can be a thing. That stuff's an alpha emitter, and you can breathe it into your lungs. So just like the radiation worker at Fukushima, if you're breathing in radon and exposing the inside of your lungs, this whole factor flips from being not worrying to being extremely worrying. So anyway, that's where quality factor comes from and why it happens, basically. The final piece is that we've got 3 sets of facts you want to be aware of. First one, very easy. The Curie, named after Marie Curie, is a historical unit of activity, and this is how we rate our sources. The second thing is that the way we measure dosage of radiation is in joules per kilogram. So the rad is a historical unit just like the rem. I won't be using rads and rems in class, but you may see them. Just understand that they basically parallel the units that we do use. So a gray is a joule per kilogram. If you get hit with a gray, it may or may not be a big unit of exposure. We'll have to see. Finally, a sievert is the most useful unit of trying to understand radiation exposure because it combines the number of joules per kilogram, so the energy basically per unit of our body, with the quality factors. It takes into account the type of radiation you've been exposed to. So what we're going to do is put all of that together in one problem and check it out right now. So what I'm going to suggest that you do in this case is to pause the deck, take a second and read this problem. What I want to do is keep my eyes on the prize. What I'm after here is ultimately joules per kilogram of body mass. So I want to get towards joules ultimately. So the way we begin is I want to take the 20 millicurie source. So 20 times 10 to the negative 3 curies. And I'm going to multiply that by 3.7 times 10 to the 10 decays per second. Let's just call it counts per second, is what's in a curie. And what I get then is 7.4 times 10 to the 8th counts per second. So now we have an understanding of what the source is doing. The second thing I'm going to want to do is to take into account the activity and how it's affected by distance. So intensity will drop off, as we talked about, as 1 over 4 pi r squared. So what that's going to do for me is I'll take my 7.4 times 10 to the 8th counts per second, and I'm going to divide it by 4 pi times the distance this person is from the source, so 4 meters, whole thing squared. And what that gives me is an intensity. So it tells me how the radiation spread out over space. So that turns out to be 3.68 times 10 to the 6 counts per second per meter squared. Finally, what I'm going to do is I'll take into account the fact that she has some body size. So I'm going to take this answer that we just got, 3.68 times 10 to the 6 counts per second per meter squared of space, and I'm going to multiply it by the actual area that she presents to the radiation. So it's the size of her as a target. So what we're going to do is just multiply by 1.5, easy enough, and what we get is 5.52 times 10 to the 6 counts per second that are actually impinging on her body. Okay, so that's all part one. What we're going to do is just to shift gears, move on. And the next thing we're going to do is now take time into account. So what we've got, if I go back, if you remember, I've got 5.52 times 10 to the 6 counts per second. So 5.52 times 10 to the 6 counts per second actually hitting her body. And then she's exposed for a certain amount of time. So if she's exposed for 4 hours a day times 4 hours, times 3,600 seconds per hour, all easy stuff. What we're going to end up with is the number of actual radiations that hit her body each day. So 7.95 times 10 to the 10, and we'll just call it radiations, like so. Okay? Now, we're almost there. What we need to do to get from radiations ultimately to her exposure in terms of joules. So what I'm going to do first is take into account what they give us in C. If 50% of the gamma rays pass through her body, that's easy enough. I divide this by a factor of 2, and so that gives us 3.97 times 10 to the 10 radiations actually hitting her body. And then what I do is I look up what's going on with a cobalt-60 source. Well, it's a gamma ray source. So if you go back to one of the very first slides we did, we talked about the fact that the gamma ray is 2.5 MeVs for every radiation. And so if she's hit with this many radiations, we know how many MeVs she's hit with. But MeVs are a tiny unit, right? They're the unit that we use when we're talking about individual radiations. What we want to do then is get to joules. So our conversion is 1.6 times 10 to the negative 13 joules per MeV. So that was just our variation on an old conversion. And what I get there is 0.0159 joules. Okay? So we're almost out of the woods and done. What we want to do finally to end up with grays is take 0.0159 joules and divide it by this person's body mass. So bigger people can absorb more radiation safely than smaller people can. And what I end up with is 2.12 times 10 to the negative 4 grays. So what you can see we've done here at the bottom is we've just taken the grays and convert them to sieverts by multiplying by a quality factor. So for gamma rays, the quality factor is equal to 1. So our number here doesn't really change. We get 2.12 times 10 to the minus 4, or 212 microsieverts of actual whole body exposure. So check it out and let's see if it really amounts to anything. So here are some numbers. We're going to look at this chart in depth in class, but a few things for consideration. The background radiation that you and I get exposed to just by being alive every year amounts to 3,650 of those microsieverts. So her exposure is not nothing, but it's not catastrophic. A chest x-ray is even greater than background radiation. It's 5,800 microsieverts. And then here's really for her consideration a thing that she'd be paying attention to if she was a real radiation worker. This is 50,000 of those microsieverts. So this amount is, in context, it's not a catastrophic amount of radiation. It's really well understood. And as we talk about this chart in class, you'll get to see this thing put together in context. So anyway, you might have some questions. Bring them with you. Good to see you. Take care. Be careful in your work with this stuff, and see you soon. Bye-bye.